Good morning students. I am Kavita Monga, lecturer physics from Government Polytechnic College, Guni Majra. Today we will solve few numerical problems on the topic of electromagnetism. To start with, let's define what is electromagnetism. So the source of electromagnetism is electricity flowing, that is current flowing through a coil of wire. So when a current flow through a coil, a magnetic field is developed around this current carrying coil, and this is the basis of electromagnetism. So with the wire oriented along a north-south line, the compass needle deflects away from this line when there is a current flowing in the wire. So when the current will flow through this wire, this needle magnetic compass it will show deflection. So this effect was first discovered by Oersted. So what is electromagnetism? A current in a wire causes a magnetic field outside of the wire. So a current carrying wire, it has a magnetic field around it. A current in one wire can cause a force on another current carrying wire. So two current carrying conductors are there, they will exert force on each other. Magnetic fields exert a force on a moving charge. So if a moving charge or a conductor, current carrying conductor is placed in magnetic field of a magnet, they will also experience a force. So magnetic field due to a straight wire, a current carrying conductor, this develops magnetic field around it. So the magnetic field due to a straight wire is inversely proportional to the distance from the wire. So as you move away from the wire, the strength of this magnetic field go on decreasing. So we can calculate this magnetic field B with this formula. This is equal to mu naught I upon 2 pi r, where I is the current flowing in this wire, r is the distance from the wire, and this constant mu naught is called the permeability of free space, and it has the value. This is equal to 4 pi into 10 raised to the power minus 7 Henry upon meter, or also Tesla meter upon ampere. So using this formula, you can find the value of magnetic field due to a straight current carrying conductor. And the direction of this magnetic field, it can be determined with the help of a right hand thumb rule. The thumb points in the direction of current, and the curling of finger will give you the direction of magnetic lines of force. So here in this example, in this figure, the direction of magnetic lines of force is anti-clockwise, and the current is moving in this direction, which is shown here. So next, what is field strength? So see this diagram, this picture. So a current carrying coil is shown, and the field due to this is depicted by these lines. So question is, what is the pictured field? Where is the pictured field the strongest? So field कहाँ पे strong है? A position पे, B पे और C पे. So options are A, B, C, or next is I don't know. The field is strongest at C. So it is strongest at C because this concentration of magnetic lines of force is maximum here. So line density is proportional to the field strength. We also define this quantity as flux. Magnetic flux is number of magnetic lines of force crossing an area. So here, since it is visible that flux is more or line density is more, that's why the field is strongest at C. So next is magnetic force on a moving charge. So what is the magnitude of a force experienced by a moving charge? So this is given here. If a moving charge moves into a magnetic field, if a charge moves into magnetic field, it will experience a force, magnetic force. The condition for the force are, must have a magnetic field present, magnetic field must be there, charge must be moving, charge must be positive or negative, and charge must be moving perpendicular to the field. And the expression of this force F, this is given as Q V cross B, where Q is magnitude of charge, V is velocity of charge, and B, this is the magnetic field of this magnet. So this is the expression of force experienced by a charge moving in magnetic field. F is Q V cross B, or F is QVB sine theta. Now what happens when this charge it experiences force? Just see, the magnetic force causes a centripetal acceleration. So what this causes, this magnetic force, it causes a centripetal acceleration, changing the direction of velocity of the particle. So what happens as a result of this force, if the magnetic field is uniform, this particle it will start moving in a circular path. Under the effect of this force, it will start moving in this circular path. So we can find the radius of this circular path using this expression, that F is QVB, and this force, this is equal to centripetal force, and centripetal force we know this is given as mv square upon r. So equating these two, we can find the value of r, that is radius of this circular path r. This is given by mv divided by q into b. M is mass, v is velocity, q is charge, and b is magnetic field. SI unit of magnetic field is Tesla. We know this, Tesla is 1 Weber upon meter square. Also this is SI unit. In CGS system, the unit of this magnetic field is Gauss, and 1 Tesla, this is equal to 10 raised to the power 4 Gauss. Now if you have to find the direction of the force experienced by this charge, the charge which is moving in magnetic field, Fleming's left hand rule we can use. So what to do? Fleming's right hand rule you can use. What to do? The index finger of right hand points in the direction of velocity. So this index finger, this points in the direction of velocity. The middle finger in the direction of magnetic field, this middle finger in the direction of magnetic field, and the thumb indicates the direction of magnetic force acting on a positive charge. So this is how you can find the direction of the force as well. Now let's solve few problems on this topic. So question is, an electron is injected with a uniform speed of 6 into 10 raised to the power 4 meter upon second at an angle of 30 degree to the magnetic field of strength 0.3 Weber upon meter square. Find the magnitude of the force on the electron. So what do you have to find? We have to find the force. What is given? Given is charge q, electron है तो electron का charge we know this is 1.6 into 10 raised to the power minus 19 coulomb. Velocity or speed of electron is given, this is 6 into 10 raised to the power 4 meter upon second. Then next, field strength is given, so field density or field strength B, this is 0.3 Weber upon meter square, and of course angle theta, this is also given, this is 30 degree. So substituting all these values in the formula of force, which is F is QVB sine theta. QVB sine theta. So substituting all these values, the value of force, it comes out to be 14.3 into 10 raised to the power minus 16 Newton. So this is the magnitude of the force acting on the electron. Next, another example. A proton moves. Now a proton is moving with a speed of 1 into 10 raised to the power 5 meter upon second through the Earth's magnetic field, which has a value of 55 micro Tesla at a particular location. When the proton moves eastward, the magnetic force is maximum, and when it moves northward, no magnetic force acts upon it. What is the magnitude and direction of the magnetic force acting on the proton? So here we have to find the magnetic force acting on proton and its direction also. Again the formula for force is QVB. Here theta is 90 degree and sine 90 we know this is 1. So force QVB, substituting the value of Q, again the charge of a proton is 1.6 into 10 to the power minus 19. Velocity is given 1 into 10 raised to the power 5, and this field is given to be 55 micro Tesla. So micro means 10 raised to the power minus 6. So calculating it, the force comes out to be 8.8 into 10 raised to the power minus 19 Newton. So this is the force experienced by a proton. Now next, about the direction. The direction cannot be determined precisely by the given information, since no force acts on the proton when it moves northward. So it is written that when it moves northward, no force is acting. So this means the angle is 0. So we can infer that the magnetic field must either go northward or southward. So next, another topic, we start with magnetic force on a current carrying conductor. So in the previous slides we discussed about a moving charge. Now next is a current carrying conductor is placed in magnetic field. So what happens? Now the force is exerted on a current carrying wire placed in a magnetic field, and its expression is given as, now F is BIL sin theta, where B is again magnetic field, L is length of the conductor, I is current in the conductor. The direction of the force is given by right hand rule. Just like the case of charge was there, moving charge, in a same manner the direction of force in current carrying conductor can be determined by the right hand rule. Now the formula of force is BIL sin theta. Using this formula, now we are going to solve few problems. So question is, a conductor 100 centimeter long carries a current of 100 ampere at right angle to a uniform magnetic field of 1 Weber upon meter square. Calculate the force and power required to move the conductor at a speed of 10 meter per second in a plane at right angle to the magnetic field. So again, now we have to find force and power. What is the force experienced by the conductor and what is the power required? So given is flux density B, this is 1 Weber upon meter square, current I, this is 100 ampere given, length of the conductor L, this is 100 centimeter which is equal to 1 meter, speed is 10 meter upon second. So the formula of force we know, F is BIL. So substituting the value of B, I and L, we get force comes out to be 100 newtons, and the power we know, power is calculated as F into V. F is force, V is velocity. Now substituting the value of force and velocity, force comes out to be 100 newton and velocity is given, this is 10 meter upon second. So this comes out to be 1000 watt. So the force experienced is 100 newton and the power is 1000 watt. Next is force between two parallel current carrying conductors. Now we will talk about force between two parallel current carrying conductors. So the force on wire 1 is due to the current in wire 1 and magnetic field produced by wire 2. So now what is happening? If we say current I1 is flowing in this conductor, then this conductor is placed in the magnetic field of this second conductor which is carrying current I2. We know straight current carrying conductor, it develops magnetic field around it. So that means both these current carrying conductors, they have magnetic field around it, fields will interfere with each other and they will exert force on each other, and this magnitude of the force, this is given as the force per unit length, this is mu naught I1 I2 upon 2 pi d. Mu naught is constant. This is permeability absolute permeability of vacuum. I1 is current through first conductor, I2 is current through second conductor, d is the distance between two conductors and L is the length. So force per unit length, this is given as mu naught I1 I2 upon 2 pi d. So now we so far we have discussed these three results. Force per unit length on two parallel wire, this is given as force per unit length is 2 k dash I1 I2 upon R, where this k dash is constant. Force on a moving charge F, this is QVB, where F is perpendicular to both V and B. So here theta is 90 degree and sin 90 is 1. So we are left only with F is QVB. Similarly, force on a wire with current I in a perpendicular B field, this is BIL. Again here theta is 90 degree, sin 90 is 1. So we are left only with force is BIL. So next let's solve few problems on this parallel wire. Now two wires are here, 1 and 2, both are carrying current. So consider two parallel wires carrying current carrying wires with the currents running in the same direction the wires are. So current is moving in same direction. So options are the wires are attracted, repelled, pushed another direction, not pushed, no net force acts, or I don't know. So what is the correct answer? Just see here. When two parallel wires, they are carrying current in same direction, the wires are attracted. The wires are attracted. How? I1 creates a field into the page at I2. So using right hand thumb rule, we can solve this problem very easily. So curling of finger, from this side the field is entering into the plane of this paper. So I1 creates a field into the page at I2 that makes a force on I2 to the left. Similarly, I2 creates a field out of the page at I1. So here fingers go inside from this side and they come outside. So the field is out of the page here in the center. So what happens now? These two fields, they will attract each other. This makes a force on I1 to the right. So the wires are attracted. So when the current is moving in same direction in the parallel wire, the wires are attracted. Next question on this problem is, force between two parallel current carrying conductor is F1. If the current in each conductor is doubled, find the force between them. So we know the expression of force. We say this F1 force between two parallel conductor is mu naught 2 I1 I2 upon 4 pi r. What is given is that current in each conductor is doubled, that is I1 and I2 are doubled. So we substitute 2 I1 and 2 I2 and we write F2 as mu naught 2 times of 2 and I1 is, it becomes 2 I1, I2 becomes it as 2 I2. So now what we get 4 and the remaining thing is same as F1. So what we get, F2 is 4 times of F1. So force will increase 4 times. That is, if the current is doubled in the conductor, the force will increase 4 times. Now next problems are on the current loop. So till now we talked of a moving charge, current carrying conductor and two parallel wires. Now next thing is the conductor. Current carrying conductor is in the form of a coil or a current loop. Now we know that when a current carrying rectangular coil or loop is placed in magnetic field, it experiences a torque. That is, it starts rotating. It experiences a torque, means these two parallel sides, it will not experience any force, and these two perpendicular sides of this coil, they will experience force F1 which is into the plane of the paper and F2 which is out of the plane of this paper. So in this way it experiences a torque, that is equal and opposite force at right angle to each other, and as a result this coil, it starts rotating. So this has many applications. So the magnitude of this torque, this is given as NBIA sin theta, where N is the number of turns in the coil, B is this field, I is the current flowing in this conductor, and theta is the angle. So we will solve few problems on this topic also. So just remember, torque is NBIA sin theta. So question is, a 20 turn square coil of side 8 mm is pivoted at the center and placed in a magnetic field of flux density 0.010 Tesla. So this is a rectangular coil, it has 20 turns and side is 8 mm and the flux density, this is 0.010 Tesla, such that two sides of coil are parallel to the field and two sides are perpendicular to the field. So two sides are parallel, two sides are perpendicular. A current of 5 milliampere is passed through the coil. So current of magnitude 5 milliampere is flowing through the coil. So question is, what is the magnitude of the torque acting on the square coil? So we have to find this magnitude of torque, and options are 1.6 into 10 to the power minus 9 Newton meter, 3.2 into 10 to the power minus 8 Newton meter, 6.4 into 10 to the power minus 8 Newton meter, or 3.2 into 10 raised to the minus 5 Newton meter. So now how to solve this question? Solution is the magnetic force on a single coil. We know force is BIL. Since theta is 90, sin 90 is 1, so we have force is BIL. So substituting the value of B, I is current, it was 5 milliampere, so converting this into ampere, it will be 5 into 10 to the power minus 3. L is length, so length, just see it was given 8 mm, so convert this into meter. So we have B, I and L. Multiplying this, the force comes out to be 4 into 10 raised to the power minus 7. Next, torque acting on the coil. So this torque tau, this is given as NBIA into sin theta. N is number of coils, 20 given tha. B I A into sin of theta. So substituting all these value, B is area, B is field was 0.01, I was current, and A is now area of that coil. So substituting these values, the value of torque come out to be 6.4 into 10 raised to the power minus 8 Newton into meter. So that is the third option is right, 6.4 into 10 raised to the power minus 8 Newton into meter. 6.4 into 10 to the power minus 8 Newton into meter. So torque can be calculated by using this formula NBIA sin of theta, or you can say torque is also force into distance, force into length of the arm. So another formula to find the torque will be force into length of the arm, that is F into R. So another problem, numerical problem, is the resistance of the loop is 0.10 ohm. So loop is shown here, its resistance is 0.10 ohm. Questions are, A question is the magnetic field strength increasing or decreasing? Second is, what is the rate of change of the magnetic field? So is the magnetic field strength increasing or decreasing, and what is the rate of change of the magnetic field? So given is the current flowing is 150 milliampere, and the side of this coil is 8 centimeter. Dimensions are given, and resistance is 0.10 ohm. So these things are given to us. So induced current is shown moving anti-clockwise. So the induced current is moving anti-clockwise. A right hand rule indicates a magnetic field out of the page. So magnetic field will be out of the page, opposing external field. Therefore, external magnetic field must have been increasing. So first question was asked whether the magnetic field strength is increasing or decreasing. So it is increasing. And second question was, what is the rate of change of the magnetic field? And the rate of change of magnetic field, this comes out to be 2.34 Tesla per second. Now next, related to this problem, that in the previous slide we saw that when a current carrying rectangular coil is placed in a magnetic field, it starts rotating. A torque acts on it and it starts rotating. So this is the principle of an electric motor. So what is an electric motor? An electric motor converts electrical energy to mechanical energy. So an electrical motor consists of a current carrying loop that rotates when placed in a magnetic field. So this is an application of the previous topic which we have studied, that when a current carrying coil is placed in magnetic field, it starts rotating. So this is your motor. Now we will solve a problem on this topic also. So example question is, the coil of an AC motor has a resistance of 4.1 ohm. The motor is plugged into an outlet where the voltage is 120 volts and the coil develops a back EMF of 118 volts when rotating at normal speed. The motor is turning a wheel find A, the current when the motor first starts up, and B, the current when the motor is operating at normal speed. So what we have to find? We have to find A, the current when the motor first starts up, and B, the current when the motor is operating at normal speed. The solution is, just see now, A first is I is given as V minus E upon R. V is potential, E is EMF developed, and R is your resistance. So substituting these values, V voltage given was 120 volts. So when it starts, no back EMF is developed. So that means at the initial point, this back EMF, this is 0. So for first A portion, what we have to find is the current when the motor first starts up. So when the motor starts up, there is no back EMF. So we had I is V minus E upon R, that is 120 volts minus 0 divided by 4.1 ohm. Resistance is given to be 4.1 ohms. So solving this, I comes out to be 29 ampere. And in B portion, this part of the question, that is the current when the motor is operating at normal speed. Now the motor is operating at normal speed, that means the back EMF has already developed. So I, V minus E upon R, this is 120 volt minus the back EMF, that is 118 volt, divided by the resistance is 4.1 ohm, and I comes out to be 0.49 ampere. So this is why the motor in your vacuum cleaner starts smoking if it gets caught on something that prevents it from turning. That means अगर कुछ फंस जाता है, so that is why the vacuum cleaner starts smoking. Now next we start with the topics of galvanometer, voltmeter and ammeter. So conversion of a galvanometer into ammeter and voltmeter. First, what is galvanometer? So a galvanometer is a device used to find direction of current and its magnitude. It has small resistance and is connected in series. So galvanometer used to detect current, small magnitude of current, direction of current, small resistance होती है and it is connected in series. What is ammeter? It is a low resistance galvanometer used to measure current in a circuit. The current to be measured must pass through it, hence it is connected in series combination. An ideal ammeter should have zero resistance. So ammeter should have low resistance, as we are required to pass the current through it. It has to measure the current, it is connected in series, and practically, ideally it should have zero resistance. So ammeter is shown here. How a galvanometer is converted into an ammeter? By connecting a shunt, that is low resistance, in parallel to it. By doing so, the resultant resistance of this combination decreases. As we know, when the resistances are connected in parallel, the output decreases, the resultant decreases. So an ammeter consists of a galvanometer with a shunt resistor. The input current IN divides with Im passing through the meter, and ISH, that is shunt, passing the shunt. It is clear from the figure. So this is your input current. So a portion of it will pass through from this, that is I input, and the rest through the shunt. So finally we get the I output. So this Im, this is given as I in divided by 1 plus Rm divided by R shunt. So how a galvanometer is converted into ammeter? By connecting a low shunt in parallel with the galvanometer. So it is shown here, and ammeter is always connected in series. So suppose a question is here now, if Rm is 50 ohms and it is required that full scale capability of 1 milliampere is to measure up to 5 ampere. So that means you have to convert a galvanometer into ammeter which can measure a current of 5 ampere. So input जो है जितना वो पहले measure कर सकता है, that is 1 milliampere, but we require it to convert it into 5 ampere. Resistance is given 50 ohms. We have to find the shunt resistance. So shunt resistance, this is Im divided by I in minus Im into Rm, substituting the value. Substituting all these values, the value of shunt resistance, it comes out to be 0.01 ohms. That is, by connecting this low resistance in parallel with this resistance, you can change its range from 1 milliampere to 5 ampere. So another example, a galvanometer has a resistance of 25 ohm